In today's video, we're going to talk about arcs, central angles, and chords. So these are all different parts of a circle and ones that you might not be familiar with. So a central angle, pretty self-explanatory. It's an angle that's formed with two radii at the center of the circle. So here you can see the central angle in pink. Now, yes, we're going to do all kinds of things with the central angle just to make sure that when you're dealing with angles in a circle, a lot of properties revolve around the angle being the central angle. Okay, it doesn't work for just any angle in the circle, but the central angle. Okay, a minor arc is less than or equal to 1/2 the circle, named with two endpoints, and the measure is equal to the central angle bounded by the arc. So here we would have arc AB. And you write it kind of with, instead of a line, you write it with like an arc, a curve over it. The measure equal to the central angle bounded by the arc. So we would say the measure of arc AB is equal to the measure of angle C. So if angle C was 45 degrees, then arc AB would also be 45 degrees. Now that's a minor arc. A major arc is more than half the circle, and we name it with 3 points total. So the two endpoints and the point in between. This just helps us distinguish and know exactly which arc we're talking about. So if you see arc AB, you know that it's the smaller arc. Arc ADB, that's this larger arc all the way around the outside. That's the major arc. Okay, so central angle, major arc, minor arc. Let's talk about a few theorems that involve all of this stuff. Okay, two arcs are congruent if and only if their central angles are congruent. So these go both ways. Maybe even you could call them definitions. So two arcs are congruent, meaning we would say BC congruent to DE, right? If and only if their central angles are congruent. So that would be angle BAC and angle DAE, right? Those being congruent to each other. So here, if this is congruent to this, then that means that is congruent to that. Which makes sense if arcs and central angles have the same measure, then if two angles are the same, then the two arcs would be the same. Okay, arcs are congruent if and only if they are cut by congruent chords. So this is kind of the same idea. If you have a chord, which remember is a line segment that's contained within a circle. If you have a chord in a circle and two chords are congruent, well, then that means that the arc lengths are congruent. So here we would say if DC is congruent to AB, then either way, right? Then arc AB is congruent to arc DC. Right, and that works both ways. Okay. Here's a good one. Chords are equally distant from the center or centers if and only if they are congruent. So we've got a center of a circle here, and these chords are equally distant from the center if and only if they are congruent. So that means that EG is congruent to EF, right? Those are the same length. So if that's true, or if BC is congruent to AD, right? If either of those are true, then the other is true. So if these two are equidistant from the center, then they're congruent to each other. If they're congruent to each other, then that means they're equidistant. So even up here, we have these two congruent chords. We know that these these chords, maybe I can do a little better than that. We know that these chords are equidistant from the center, right? So, because they're equal to each other. And here we know that these chords are equidistant from the center, so they are equal to each other. Either way. And just note that this forms a right triangle. If you wanted to prove something like this, and we'll look at this a little more later, if you wanted to prove something like this, you could maybe look at drawing some radii, right? Here and here. So that creates two congruent right triangles by hypotenuse leg, which means because in the distance, it is perpendicular, right? So when I say a distance, I'm talking about the line that's perpendicular to that chord. So then we have this, we have these two triangles as congruent. And then again, if you know these lengths are the same, the radii are all the same. So then you have these two right triangles congruent to these two right triangles. So then that would mean that these sides are all congruent as well, right? That and that and that and that are all congruent. So then the chords are congruent. And you could do the same in reverse, right? So that's just a quick proof. It's not really a whole lot, but it's something to think about. Okay, let's look at this last theorem. A diameter that is perpendicular to a chord bisects the chord and its arc. Okay, how could we prove that? Well, we'll do it similarly to how I just looked at the last, the proof of the last example. A diameter that is perpendicular to a chord. So we're saying that this is perpendicular right here. Bisects the chord and its arc. So we know that AB is a diameter. And we're trying to prove that we want to show that CE is congruent to ED. Or that CE equals ED, right? That's kind of what we're looking to show here. How can we do that? Well, again, if I draw two radii, one here and one there, and again, that's the radius of the circle, so I know that these are congruent. Okay, and now I have a hypotenuse leg. This is congruent to itself. That means these two triangles are congruent, right? These two triangles right here are congruent. So I can kind of, we're not really saying a lot, but I know that triangle, let's see, CEO is congruent to triangle DEO by hypotenuse leg. And so then I can say that CE is congruent to ED by congruent parts of congruent, corresponding parts of congruent triangles are congruent, right? CP, CT, C. Corresponding parts, congruent triangles are congruent. So again, I'm not asking you to prove anything, but just from my perspective, just to show you why that's true. So we would say if AB is perpendicular to CD, then CE is congruent to ED. So there you go. And know that it only works the first way, right? It doesn't necessarily work. Just because a chord is bisected doesn't necessarily mean that that is congruent. It has to be the diameter and it has to be perpendicular, okay? Okay, let's look at some examples real quick. Find the measure of each arc or angle below. Well, arc BC, the central angle here is 80 degrees, so BC is 80 degrees. Angle 1, well, arc AB is 70 degrees, so that angle would also be 70 degrees. AC, okay, which one is it? Is it this way or that way? Well, let's see, this arc, and let's not just rely on our eyes, right? This arc right here is 70 plus 80, so this arc would be 150. Total around a circle is 360. So that means this arc right here would be 210 degrees. So remember, AC is the minor arc, which means it's the arc that is less than half. Well, 150 is less than half, so AC is 150 degrees. ADB, we could try to calculate this. So there's two ways. We know that ADC is 210. We know that BC is 80, so then 210 plus 80 is 290. We also know that the total measure of the circle is 360, and ADB is everything but this 70 degrees right here. So we could say, maybe on one hand, 210 plus 80 is 290, or we could say 360 minus 70 is 290. Either of those would be acceptable answers, or acceptable ways to find ADB. It's the same measure, so that feels pretty good. Okay, let's look at another example. If PS equals 12, PS is 12, and TR is 15, we want to find QR. So we need to look at all of these angle measures here. What are they telling me? Well, I know that this is 50 degrees and this is 20 degrees. So this whole arc right here, arc SP, is 70 degrees, right? So if that's 70 degrees, well, that's the same as QR. So I don't even need the fact that TR is 15. I can just say PS equals QR. So QR is 12, sorry. Because we knew that PS and QR were equal to each other, they had equal angle measures, so those chords must be congruent. A few more examples. In circle A, SQ is 12, SQ is 12. And AT is 8. Find PR. Okay, so if SQ is 12, then that means, and this is perpendicular, right? And where PR is a line, so that means it must be a diameter, right? That means that this has been bisected, right? And you can even see that because this is an isosceles triangle, right? It has the same radius AS and AQ. So that's going to bisect here. Okay, so since that's bisected, that means that S, whatever this is, right? Oops. This point right here, that's 6. And so maybe we can bust it out. This triangle right here, here's A, here's S, and here's that dot. S dot is 6, and A, oh, this is T. Oops, sorry. Sorry, T. ST is 6, AT is 8. Then that means AS must be, well, this looks like a 3, 4, 5 right triangle. So AS must be 10. And that's the that's the radius of the circle, right? If that's 10, well, if that's 10, well, then AR would be 10. And PR is, so we say AS equals AR because those are both radii. And we know that PR is twice of AR. So PR must be 2 times 10 or 20. Okay, so the trick there mostly is recognizing, one, that you have a right triangle right here, that you can, that this diameter bisects SQ, and then recognizing that AS and AR are equivalent or congruent. Okay, last example, in circle O, FL is 3, FL is 3, GO is 5, OP is 4, find HJ, find HJ. Okay. GO is 5, so the radius is 5. Okay. I'm looking for HJ. Well, this looks like, okay, so I kind of got ahead of myself. So let's just look at what we know. I don't know that OL or OP is congruent, so I can't necessarily say that GF and HJ are congruent right now. What I know that I can say for sure is that GO, the radius, is the same here as it would be over here. So GO equals OJ. I can definitely say that. I feel really confident because these are both radii, okay? Now, I know that if I've got this line right here, right, this OP, that I can find, I've got a right triangle right here, right? This is even a 3, 4, 5 right triangle. Okay, now is HP equal to PJ? Well, you know, there's a lot of ways you could prove this, but yeah, you could simply extend this line and make it a radius, or you could say, well, I know I could create a radius right here. That length would be 5, and then this length would also be 3. So then HJ is 3 plus 3, or 6. Okay, so the key there, I mean, that's kind of a lot to think about, but if you just look at the fact that we have a radius, it's 5. We have another radius, it's 5. We have this length OP, which is 4. We can find a 3, 4, 5 right triangle. And then, even then, you could say, well, that means these are equidistant from each other and all of that stuff. But instead, it's easiest to probably just say, I know that this is perpendicular. This would easily form a radius. So this is 3, this is 3. Or you could use the other radius to make another right triangle, find the leg of 3, and then say it's just 6. A lot of ways to go about that. Okay, so big key things to note. All those theorems that we went over on the first page, right? Be careful when you're working with central angles, when you're working with chord lengths, when you're working with arc lengths. It's a lot to keep in your brain, but take it step by step. Make sure you're using reasons for each step, and really focus, I would say, on the radius is super, super important when it comes to solving these things and finding these things and using your intuition. That's it for this video. Good luck. I'll see you in the next one.